Hello. Good evening. Hey, I can hear myself now. All right, welcome everyone. Thanks for coming out to Café tonight. Are you ready to get things started? Oh, we've got a live crowd here tonight. For those of you joining us online, I assume you were. We could hear it all the way from wherever you are watching tonight. Hey, my name is Brad Peroni, and I'm on the team here at the Science Center. I'd like to thank you all for joining us this evening. Before I introduce tonight's speaker, I would like to take a moment to thank PPG for being our presenting sponsor. And I'd like to thank all the Café Sci attendees and viewers online who have made contributions of their own to support Café Sci. And if you would like to do that, we can certainly talk after the show, but one of the best things you can do to support Café Sci is to come back next month with 2 or 3 friends, and the month after that, bring a few more friends, and before you know it, we'll have to build a whole new wing of the museum just to fit the Café Sci audience in here. So let's see some exponential growth here for our audience. Tonight's presentation will be a talk followed by Q&A. So for those of us here on site at the Science Center, we'll pass around a microphone. We'll bring it to you, so please do wait for us to get to that microphone, because that's going to help the people online hear your question also. And for those of you joining us online, you can find a Q&A box at the bottom of your Zoom screen, and you can enter your questions at any point during the talk. And if you wanted to bring someone, they couldn't make it, don't worry, this talk is being recorded. We're going to post it on the Science Center YouTube channel in the coming days. But it is now my honor to introduce tonight's speaker, Dr. Bruce Banerdt. Dr. Banerdt is a planetary geophysicist at NASA's Jet Propulsion Laboratory and principal investigator of the InSight mission. And he was so kind as to bring stickers for the InSight mission, and you can find some at the exit you can get on the way out. Make sure you take a handful of those. He holds a BS in physics and a PhD in geophysics from the University of Southern California, and has worked in the Earth and Space Sciences Division of the Jet Propulsion Laboratory since 1977. Dr. Banerdt has served on numerous NASA, DLR, and National Academy of Sciences advisory panels on planetary and space science, and has published over 140 journal articles, reports, and book chapters. His research focuses on the geological history of the planet Mars and geophysical investigations of the interiors of terrestrial planets using analyses of gravity, magnetic, topographic, and seismic data. In addition to a staggering number of unselected planetary instrument and mission proposals, he has participated in several planetary flight instrument teams, including the MOLA altimeter on Mars Global Surveyor and the imaging radar on Magellan. He served as project scientist for the Spirit and Opportunity rovers for 6 years before heading up the successful NASA Discovery Program proposal for the InSight mission. And he's been the principal investigator for InSight since 2011. And with that, I would like for you all to welcome to the stage your speaker tonight, Dr. Bruce Banerdt.
Thanks, Brad. Thank you all for coming out tonight to listen to me talk about my favorite subject, although I kind of have a hard time talking about the InSight mission because nobody will give me a 3-hour time slot. So I just try to talk 3 times faster, and then I can fit everything else in. So let me know if I'm talking too fast. And we can stay here until 9 o'clock. Okay, so I'm going to talk today about the InSight mission, journey to the center of Mars. And I say that because the InSight mission was designed to look deep down into Mars, all the way to its core. It's a little bit of a different kind of a mission than most of the Mars missions that have gone before. The goal of the mission, and we had to sell this to NASA. When I say it was a NASA proposal, it's not a proposal from NASA, it was a proposal to NASA, was to understand the formation of terrestrial planets, of rocky planets. Not interested in Jupiter, Uranus, Neptune kind of, but the rocky planets are really the ones that interest me the most. And in order to do that, we investigate the interior structure. How do you get to the history through interior structure? Well, it turns out, first of all, how are we going to do that? We're going to do that with 3 methods. Seismology, which is the way that we know most of what we know about the inside of the Earth. Precision tracking, and that seems like a little bit of a weird thing to do, tracking the spacecraft really precisely. But it turns out if you do that, you can measure the wobble of the rotation axis, and that tells you all kinds of things about the deep interior of the planet. And heat flow. You know anything about InSight, you know that's a very sad subject, and I'm not going to talk about it today because I'll probably cry. So we're not going to talk about heat flow today. It didn't work. Enough said. So anyway, the reason why we are interested in the deep interior of a planet is because it really affects everything that goes on at the surface. A planet is actually a heat engine. The heat that's produced in the center of the planet, and it's produced by the decay of radioactive elements, it heats things up, it melts the core, but it also causes the rest of the planet to move and do stuff. Okay, so heat is energy. As the heat leaves the planet, it does stuff. It does work. It moves around the plates on the Earth. It pushes up our mountain belts. It opens up our deep canyons. It actually supplies all the materials that we have on the surface of the Earth. It supplies ores that we dig out of the ground, but also supplies the air that we breathe, the water that we drink. All that's come from the interior of the planet. So it really provides all the necessary conditions for life to exist on the surface of the planet. And so understanding how an interior works helps us to understand how life might occur on other planets and how those planets might be habitable, might be places where life can continue. And so that's one of the ways that we sell this kind of stuff. I don't care about life on other planets. I care about rocks. I'm kind of a geology hermit, but other people care about life on other planets, and this actually is relevant. So the thing that interests me is that the interior planet keeps the fingerprints of things that happened 4.5 billion years ago. So when the planet accreted from the dust in the solar nebula, it started clumping up, and as it clumped up, it got hotter and hotter and got bigger and bigger as the gravity pulled in stuff. And then what happens is something called differentiation. So instead of having a planet that's all made up of carbonaceous chondrite meteorite, which if you pick up a rock, it's not going to be the minerals that are in a meteorite. It all melts, and once it melts, it separates, just like cream separates or whatever, and that's called differentiation. The heavy stuff, like the iron, sinks to the middle. The light stuff, which are the rocks we have, when you pick up a rock, that's actually light for a geologist. They all float to the top, and you get a stratified planet. And the way that happens affects everything that goes on afterwards. And all that happens in the first few tens of millions of years. By the time you get to 100 million years, it's basically a mature planet, and then the rest of it is just kind of smudging up the fingerprints. So when we measure the things that go on inside the planet, we are actually measuring the results of that first few tens of millions of years, and it's helping us understand how that planet formed and how planets in general form. So that's really the sort of the deep scientific background of the InSight mission. So I'm not going to talk about it from that standpoint. I'm going to talk about it from the standpoint of being a time machine. So first of all, it goes back 4.5 billion years, just like I said, to look at the processes that happened when the planet first formed, and it's measuring the basic building blocks. So on Earth, we have hundreds of seismometers all over the planet. We have thousands of places where we measure the heat flow. We're measuring the wobble of the Earth's rotation all the time, but NASA's not really willing to give me $1 trillion to reproduce out on Mars. They're willing to give me one spacecraft, one lander, one seismometer, one heat flow probe, and one radio to track. And so we have to be a little bit less ambitious. So we just really want to measure the basic building blocks of the planet. And I'll talk about that in a minute. But first of all, think of InSight as a time machine, not going back 4.5 billion years. That might be a little bit scary. We're going to adjust the dial and only go back about 120, 130 years, back to the dawn of the 20th century, a little bit before. And do the same stuff that Earth science was doing back then. Around the year 1900, we knew Earth had a core because it was too heavy to be solid rock. But other than that, we really didn't know much of anything about what was going on under our feet. Once you got down more than a handful of miles that you can get down in a mine shaft, we didn't know much about what was going on in the Earth. And we're kind of at that place at Mars, or at least we were 10 years ago when I wrote this proposal. So we want to answer the same questions as Earth scientists were trying to answer at the dawn of the 20th century, which was, how thick is the crust? What's the size and the density of the core? What's the structure of the mantle? So we had an idea that it had kind of these divisions, but we didn't really know much about it. And then what's the distribution of seismicity? And that was even a question that maybe people hadn't even thought of very much until about 1900. So we're going to go back and try to reproduce what scientists did on Earth 100 years ago. Okay, so go back to 1889, which was the first remote detection of an earthquake. Okay, so people have been detecting earthquakes on the Earth for millennia, right? It's easy to detect an earthquake when rocks fall on your head and stuff like that. But how do you scientifically actually measure an earthquake that happens somewhere else when it's not actually shaking under your feet? And the first time that was done on the Earth was in 1889, and it was an earthquake in Tokyo that was recorded in Germany by a guy named Ernst von Reuben. I don't know how to pronounce his name, Reuben Paschwitz or something like that. And he was actually had a device that was measuring the gravitational attraction of the moon as it went overhead. And the gravity would move this needle on a moving piece of paper. And he had this little kind of glitchy thing here. And he didn't really know what it was. But then about a month and a half later, the steamship came from Tokyo or whatever and said there was an earthquake on this date at this time, and he realized that this glitch that he had on his record had happened about an hour later. And so he wrote that up. And so this is the first time that a earthquake was recorded remotely from a distance other than actually being able to feel it shaking. So that's the sort of the birth of birth of seismology. So in 1906, about 16, 17 years later, by then seismology had come far enough that we were able to detect the core of the Earth by looking at the motion, motion of seismic waves through the Earth. They go down, they bounce off the core, they get reflected by the core, and by looking at that, they could figure out how big the core was. And they did it with this device here, which weighs about 1,200 pounds, which is a little bit too heavy to carry on a lander to Mars. But fortunately, we've gotten better at that. And so now we know how big the core is. A few years later, we were able to get to the thickness of the crust by this guy named Andrija Mohorovičić, and we call it to this day, we call the boundary between the crust and the mantle the Moho, in honor of Andrija here. And he was able to, again, look at the bounces of seismic waves off the bottom of the crust coming back up in Croatia, and able to determine how thick the crust was in Croatia. And of course, after that, many other people reproduced those kinds of measurements all over the Earth. In 1936, so this is what, another 15, 20 years later, the Earth's inner core was detected by seismology, by Inge Lehmann. And just again, looking at the paths of seismic waves through the Earth, looking at where you detected them, what time you detected them, and then sort of tracing them back through the Earth and figuring out how they must have gotten there. She was able to deduce that there was a solid inner core, something that was bouncing these waves off of inside this liquid core. The interesting thing was that it was pretty much widely dismissed until the 1950s, when some male geophysicists were able to reproduce the results. So that's really not surprising. I mean, it's not surprising that she wasn't believed, because after all, she was Danish. Okay. So fortunately, we've come a long way, and Danes are accepted into the scientific field these days. But anyway, so 1941, Gutenberg and Richter of the famous Richter scale, published the first distribution of seismicity on the Earth, sort of the global seismicity, the distribution of where earthquakes occur. And this was a really important step forward on understanding the properties of the Earth and the activity of the Earth. And of course, you can see these quakes are all concentrated in these lines, these belts. Eventually, that was interpreted and understood in terms of plate tectonics. So this is one of the basic building blocks of our current understanding of the heat engine of the Earth, which is basically a plate tectonic engine where the hot stuff comes up at the mid-ocean ridges, the cold crust gets pulled back down at the trenches, at the boundaries, and that whole cycle there is essentially the pistons of the heat engine of the Earth. And most of the geology that you see on the surfaces are mountains, are rift zones, our volcanoes are all tied to this heat engine. Okay, so a few years later, 1949, they published a second work which looked not at the geographical distribution of earthquakes, but at the distribution of size. So how many earthquakes do you see on the Earth that are magnitude 5 versus magnitude 6 versus magnitude 7? And they found that there was a logarithmic distribution where there was something like 30 more magnitude 6s than there were magnitude 5s, 30 more magnitude 8s than there were magnitude 7s. And so it was a power law that had a slope of about 1. So it was predictable how many quakes that you would have. If you got one magnitude 5 quake, you could expect about 30 times more magnitude 4 quakes. And this was predictable all over the Earth. And then we can start looking at the physical processes that would set up this kind of a distribution. So it took about 60 years to go from that first detection of an earthquake to pretty much a basic understanding of the entire Earth and its activity. We had the chutzpah to say we could do that in 2 years. 60 years, no, 2 years, one seismometer, we can do that, which was a little bit daring. I spent about 20 years trying to convince my colleagues and then NASA that we could even do seismology with a single seismometer on Mars. If you know anything about seismology, you know you need at least 3, right, to be able to triangulate in on an epicenter from your records. But there's a lot of clever stuff you can do, it turns out, when you've got computers and graduate students and things like that to get the same information using different methods. And people have been thinking about seismology and developing methods in seismology now for 130 years. And so there's actually a lot of stuff that we can do. So we said we could do it in 2 years, which is 1 Mars year, coincidentally. And spoiler alert, we were able to do it. So with the data we got in the first 2 years, we were able actually to do those things. We were able to get the crustal thickness, we were able to get the core size, we were able to get the core density. There's actually, when we put in our proposal, there were 8 what we call level 1 requirements. So basically each one of those was a number. So I proposed that we would be able to get those 8 numbers. The mission costs about $800 million. That's $100 million per number. Okay, so if you ever wonder how much a number costs, I'll sell you one for $100 million. Okay, so, and we've been continuing to refine it for the last 2 years. We've been on Mars now for almost 4 years. It'll be 4 years later this month. So here's a comparative structure of the Earth, the Moon, and Mars. So to me, when I put this figure together for the Encyclopedia of the Solar System in 2014. The thing about this figure that always jumped out at me was the fact that these question marks. Okay, so you've got numbers everywhere. You got numbers for the Earth that are really good. You got numbers for the Moon that are pretty good. We got those using seismology on Apollo back in the 1970s. But for Mars, all we have are question marks. These are all, they're actually guesses, okay? A lot of what scientists do is they guess. A PhD is a license to make stuff up, right? But you do it in an intelligent way, so you have at least a chance when somebody measures it that it's gonna actually work out. So these are all guesses. They're extrapolations from what we know about the Earth and the Moon and using models of how things would extrapolate to another planet. So we didn't actually know these things, but we kind of thought we sort of knew them. But there's nothing like a measurement, so let's see what we can do. So this is how we did it. This is the InSight spacecraft. We only had 3 instruments. NASA doesn't like it if you propose a lot of instruments because instruments are always a pain in the neck. They always break, they always go wrong. So we said, oh, we only have 3 instruments, and one of them is not even an instrument, it's a radio. We had the seismometer over there on the left. You can't see it, but it's underneath there. We had a heat flow probe. I promised I wasn't going to talk about that. I'm not going to talk about that. And we had these, what we call medium gain antennas, MGAs, which actually communicated with the Deep Space Network and allowed us to track the spacecraft. And I don't think I'm going to be able to talk fast enough to talk about that tonight, but we'll see. But we had, okay, so first of all, yeah, the mole's actually way up there. I'm going to cry. Okay, so but we had a lot of other stuff as well. We had all these sensors to measure the environment. We have a weather station that gives us pressure, temperature, wind. We have a magnetometer. We have a camera, all this stuff. And none of it was related directly to the science that we did. It was all kind of, we didn't call them instruments, we called them sensors. And they were there to support the seismometer. And why do we need to support the seismometer with a weather station? It's because the seismometer measures vibrations, and anything that causes a vibration is going to be picked up by the seismometer. And if you're a seismologist, you know that a seismometer measures almost everything in the universe better than it measures a vibration. The seismometers are sensitive enough that if you walk up next to it, the gravity from your body will actually cause the needle to move, okay? That's how sensitive these seismometers are. And so we have to measure everything that's happening so that we know that those things aren't our signal. So here's a seismometer. This is what you can see on the surface. It's called our BBB, that stands for Very Broadband Sensor. That just means that it measures it at a lot of frequencies, from about 1 cycle every 100 seconds up to about 100 cycles per second. So that's a difficult thing to do, but these things do it. And like I said, we need to try to keep it from getting affected by everything else. So we actually isolate it. We isolate it a bunch of different ways. First, we have this windshield over it, and then you can cut that away. And on the inside, that's actually a thermos bottle. It's not really it's a soft thermos bottle. It's made out of foil, but it turns out on Mars, its atmosphere is thin enough that if you put two walls and let the CO2 go in, as long as you don't have holes so it can go in and out, it insulates just about as well as a vacuum bottle. So that's our thermal protection. Then inside that, we have this gold spheroid thing. That's a real vacuum enclosure that keeps the pressure variations from affecting the seismometer. It insulates it again in temperature. And so this is where the VBBs live. There they are, down inside there. This is the heart of our mission, is these 3 little sensors. They measure the motion in 3 different directions so we can tell exactly what's happening on Mars. And so this is our sensor. It's about the size of my fist. And this thing is an amazing instrument. So what this does is it measures vibrations. And this is a complicated chart, but this is sort of the amplitude of the vibration, okay, in meters per second squared. And we're down here around 10 to the minus 10. That is roughly the diameter of a hydrogen atom. So this is the green stuff is what we actually measured on Mars. The black was our theoretical curve, what we thought we could do with it. This gray curve up here and the orange curve, that's as quiet as it ever gets on the Earth anywhere. If you go to the quietest point on the Earth, in the middle of a continent somewhere, it never gets any quieter than up here around 10 to the minus 7, 10 to the minus 8. So we're actually able to measure things 1,000 times more sensitively than is worth doing on the Earth, because it's always going to be noisier than that. But it turns out Mars, because it doesn't have a thick atmosphere, doesn't have an ocean, we can actually take advantage of this 1,000 times more sensitive instrument that's measuring vibrations on the level of an atom to actually measure vibrations from Mars quakes that are going through the entire planet. And it's not even magic. It seems like magic, but it's not. Okay, so first detection of a distant quake, it was done in 1889 by von Weber-Paschwitz. We did it in 2019, and the InSight MQS stands for Mars Quake Service. That's just our team that actually analyzes the seismic data and finds quakes. This was event S0128A. That means that this is a seismic event. It happened on the 128th sol, or day of the mission, and A means it was the first one that day. Turns out this was the first one we measured anywhere, which was kind of interesting because we landed, we took about 3 months, about 90 sols or so, to put the seismometer on the ground, get it all covered up, get it nice and snug, get it tested out, and then we sat and we listened. We sat there for another 3 months with nothing happening. And I promised everybody for like I said, 20 years that we could do seismology on Mars. Is, oh yeah, there's going to be Mars quakes, no doubt about that. And I finally convinced everybody, and then here I was waking up every morning, going to my computer, looking at the data, just noise, just noise, just noise. And I got to say, I was getting a little bit nervous that maybe this was not going to work out for me, but it did work out. So Sol 128, we got our first Mars quake. You can see the vibrations down here. This is what we call a spectrogram, and this tells us a lot more about the event than just the wiggles that you see on a seismogram. It tells you the spectral content is a function of frequency and time and amplitude all at the same time, and that's what a seismologist actually uses to do their job. And this big blotch here is the Mars quake. So it was pretty close. It was we measure things in degrees, which are like degrees of latitude along the surface. 7.8 degrees is about 300, 400 kilometers away, and it's a small Mars quake, but it was very welcome. Fortunately, about 2 months later, we saw a bigger Mars quake, one that we could actually do something with. Here, you can see on here, you can see the P wave, you can see the S wave. Those are kind of our bread and butter seismologists, the primary wave, the compressional wave, and then the secondary wave, which is the shear wave, the transverse wave. And once you have those, you can start getting distances. You can look at things like polarization, which is the direction that the waves are vibrating in. And those are the kinds of things that allow us to locate the quake, determine the velocities. The velocities are the things that tells us about the composition and the path that it took. So this is, like I said, this is about, at this point, 8 months into the mission, and we finally get a quake that we can start to work with. It turns out that we landed during the noisy season on Mars. This is at the time when Mars's thin atmosphere is still enough to have turbulence. It's still enough to affect the seismometer at those very, very fine levels. Okay, so on a noisy day on Mars, that noise is about at the same level as the Earth's quietest time. But Mars quakes are small. Mars is not as active as the Earth, as I'll show you in a minute. So that's why we couldn't see these things. They were getting drowned out by the atmospheric noise. But it turns out for about half the year, all that atmospheric activity just kind of collapses at night. So you come up to 5 o'clock in the evening, and suddenly the air stops moving, and the background noise gets down to that 10 to the minus 10 meters per second squared level, and finally we can see these very small quakes coming through. There are some big quakes that come up above that noise, but it took us 3 or 4 years to get those because they're pretty rare. Okay, so next we want the crustal thickness. That's kind of the first building block of the planet. And the crustal thickness, that tells you something about the differentiation of the planet. That's kind of the scum that kind of floats to the surface. So we're all just kind of living on the scum of the Earth, as a term. So That's a geophysicist view of the Earth. It's kind of negative, I guess. Oh well. Anyway, so that tells us the degree of differentiation, how much of the planet melted early on to create this flotation layer up at the very, very top. And so that's a very important number, worth $100 million to NASA. We were able to do it by looking at, let's see, have I gone too far? Okay, actually looking at the way waves come up, and they get refracted and reflected just like optical waves. If you've ever taken an optics class in college or high school, you know that light gets bent when it goes from a material with one index of refraction to a material with a different index of refraction, like going from air to glass. Okay, so the same thing happens to seismic waves when it goes from very dense rocks to rocks that are not so dense. It gets bent. And so there are different paths that it can take, plus it bounces off of these things. And by looking at the difference in the arrival of waves coming in through these different paths, we can actually measure the thickness of these layers. And we're able to do this. This is the data. It looks like garbage, but it's good enough. Okay, we were able to convince some very skeptical terrestrial seismologists that these were actually signals and not just noise. So it showed us that the thickness beneath our lander was about 40 kilometers. That was pretty much within the bounds of what we had imagined. We thought it was going to be between about 30 kilometers at the thinnest and maybe 60 kilometers at the thickest. 40 kilometers is kind of in the middle, so that kind of validates what we thought, which is always, that's kind of a cool feeling. Yeah, we measured it, we were right, hey, yay us. Okay, and we are actually able to measure some other layers in that crust, not layers like you see in the Grand Canyon, but these are thick layers, 10 kilometers thick layers that are probably due to the way the crust formed. Has a primary crust, and then you have a lot of lava flows piling up, and then you have meteors coming in, breaking things up. So you have different layers of things, and that is all connected to the geological history of Mars. Yeah, and I already said this. So now we have a model of the crust. We can actually extrapolate that all over the planet, it turns out, because we have gravity data, and gravity tells us where the relatively low density crust is thin, where it's thicker. So we already knew how the crust varied on Mars, but we just didn't know couldn't pin it to a given thickness. Now we know how thick it is and not just how it varies. All right. You have another way to get at the crustal thickness. That gives what I talked about before was getting the thickness straight underneath the lander. These are seismic waves that are coming up from the beneath and bouncing back and forth and getting refracted. This is something called surface waves. These are waves that are kind of trapped in the surface layer. When you have a really big quake, it develops these surface waves. You can't actually see them for smaller quakes. Turns out we went 3 years seeing nothing bigger than about a magnitude 3.5, and then suddenly 3 years into the mission, we've gotten about a half a dozen magnitude 4 to 5 quakes, which is interesting. We don't know why there's a clustering like that, but these big quakes have given us a bunch of information, including the surface wave stuff, which gives us an average value of the crust between where the event occurred, the epicenter, and our location. And it turns out that it verified the thickness of the crust, but we didn't see this uppermost layer, this low velocity, low density layer. And we think that that is something that is particular at InSight, and it's maybe related to some of the impact history around there, actually breaking up the rocks more there than in the volcanic plains that waves went through. So we're starting to get not just a single point measurement, but seeing Mars as a planet with diversity, which is really, really exciting. Okay, then we want to get the core size. That's the next big building block. We got the crust, got the mantle, we got the core. The core is a little bit easier to investigate than the mantle, even though it's deeper, because iron is a really big contrast in properties from rock. And so we can actually look at waves. They bounce very, very well off of the boundary between the molten core and the solid mantle. And so we're able to pick up these bounces from a series of these quakes. And it's pretty simple. It's just a timing thing, you know. You go pop on the surface, the vibrations go down, they bounce, they come back up. You just measure that time it takes to do that. You infer the velocity from a fairly complicated process, and the time divided by the velocity. I don't remember which way the division goes, but the velocity and the time, you get the distance, right? So we're able to get that. We bounce it off the core, and turns out the core radius is 1,830 kilometers, give or take. But that is really big, okay? We thought it was going to be 1,700 kilometers, maybe 1,800 kilometers. Doesn't sound like that much more, but from a physics standpoint, that's a lot, because as the core gets bigger, we know what the mass of the core is. You know, we can measure that using gravity. But so if the core gets bigger, the density has to go down. It has to get the material has to get lighter. So the core density is 6,000 kilograms per cubic meter, which is much less than a solid, not a solid, a pure iron nickel core. Pure iron nickel core is about 6,500. So how do you get that density down? You dissolve stuff in it. You dissolve carbon, you can dissolve sulfur, you dissolve oxygen. These are all things that get dissolved in this molten iron. You can dissolve things in molten iron just like you dissolve things in water. And since these are lighter elements, it decreases the density of that material. But it also does something else. It also changes the melting temperature. Just like when you dissolve salt in water, it changes the melting temperature. So the melting temperature goes down, so ice melts at a cooler temperature. This makes it possible for the core of Mars to be molten today. If we didn't have these elements in the core, Mars would have a solid core, not a liquid core. And that has implications for when a magnetic field could have occurred on Mars, or whether a magnetic field could still occur on Mars. Today, there's no magnetic field on Mars, but we have evidence that it was there in the past. This is going to help us understand when that magnetic field could have been present and why it shut down. So there's lots of implications here, because that magnetic field is responsible for keeping the atmosphere. If the magnetic field collapses, suddenly the solar wind is stripping away the top of the atmosphere, and you have a thin atmosphere on Mars like you do today. If the magnetic field had stayed there, it would have had a thick atmosphere, something close to the atmospheric pressure of Earth today, and there may have been little green men running around on Mars, but that didn't happen. So this is all kind of connected together. It's a really, definitely worth $100 million. Oh, and by the way, this is something that we didn't expect. Well, some people really enjoy having things work out the way they like, but turns out for a scientist, really, is you want to break the theories. That's sort of the dream of every experimentalist, is to make a measurement and all the theories are wrong, so they have to go back to the drawing board. That's just, again, kind of a perverse joy in advancing knowledge by kind of taking the air out of people who maybe thought a little bit more of themselves than they should have. Anyway, so again, we can look at the core another way, not just bounces off the core. We can actually look at waves that travel through the core. So since seismic waves, the P waves at least, are compressional waves, they're basically sound waves that are moving through material, and those can move through liquid as well as solid. And so you have waves that can actually travel through the core and come back up the other side. And when that happens, those waves are picking up the properties of the material that they went through. So this is something that's still tentative. We've written it up. We've submitted it to a journal. It's under peer review now, and if they agree that this is a valid measurement, it'll actually allow us to get a little bit more insight into which of those elements are actually in the core and how that goes together with our geochemical theories of core formation. So we're kind of up to Inge Lehmann in 1936 at this point, All we need to do now is figure out where things happen on Mars, and we're starting to get that as well. It's not the same picture of the Earth as the Earth. It turns out on Mars, we don't have plate tectonics. We didn't expect plate tectonics, and we didn't find plate tectonics. What we found was that most of the seismic activity we found is concentrated in a single area, a place called Cerberus Fossae. Cerberus is like a three-headed dog that guarded the gates of hell, I think. And fossae just means cracks. So this is a series of cracks or faults, and we knew that these were there from orbit. And there's cracks and faults all over Mars. Mars has a very old surface, but these were actually very special. We knew that these were actually young from a geological standpoint because there were lava flows and there were evidence of flooding, and those surfaces had very few or almost no craters on them at all. So most of Mars is very cratered. There are things hitting Mars all the time. And so you can actually tell how old the surface is, how long it's been sitting there, by how many craters it has in it. And the surfaces around Cerberus Fossae that were cut by these faults had very few craters, and we could tell that they were no more than 500,000 years old. You know, practically a baby, right? 500,000 years old. But we didn't really know whether they were still active, and this was a really, really, again, gratifying in terms of verifying what we thought we knew, was that this was the place where we started seeing these quakes. That second quake I told you about, the one that was finally large enough to do work with, that was from Cerberus Fossae. And about 80% of the activity that we see is in this one place. The rest of it is just kind of scattered around the planet. We don't know completely how the seismic activity of Mars is distributed because the core actually kind of shadows a lot of the planet from us. About a third of the planet is not directly visible to us seismically because the core, it doesn't reflect all this stuff back, but when stuff gets into the core, it bends it, right? It refracts it, and so there's a shadow zone. We can see some things that go through the core, but not everything. The reason why we can see some of these guys over here, this is almost on the other side of the planet, is because we actually have things that go down and come back up and bounce off the crust, and they kind of take a detour around the core. So there are ways to get over there, but mostly what we know about is this half of Mars, and we know that there's more or less a random distribution except for this stuff here. So right now, most of Mars's activity is concentrated in one place. We think it's probably because there's a plume of hot material coming up there, and that might move around as a function of time. Maybe if we come back, I don't know, 100 million years from now, it may be doing it somewhere else. But that's very different than the Earth, and it's more in line with the way a smaller, cooler planet would be expected to act. Even though Mars' core is liquid, it's actually a much colder planet than Earth. It has lost most of its heat. It doesn't have as much volume. The smaller something is, the less surface area it has to radiate stuff off. And so Mars has a different tectonic character than the Earth does. It has what we call a hotspot activity rather than plate tectonic activity. So this is all kind of coming together, and our theories are more or less converging to something that makes sense. And these measurements that we're making are modifying those theories. Except for the core, they're not completely upsetting things, but we're working on trying to make our core measurements fit in, and we've got some ideas on that, but that's still a few years down the road. Okay, so here's the sort of the last piece in this set of measurements that we want to make. What is the seismic activity of Mars? I actually worked on a paper with some co-authors back in the early 1990s, and we estimated what the seismic activity of Mars might be today. And we did that by looking at all the faults going back 3-4 billion years on Mars, what the dates were of them, and looked at how it was dropping off with time, and we just drew a line through, okay, so there was this many faults that were being made 4 billion years ago, there were this many faults being made. 2 billion years ago, there were this many faults being made. 500 million years ago, and just draw a line through that, and kind of squint your eyes a little bit, and you get to the present, and you come up with a number. And this is the number that we came up with. This red line here. That was our pre-mission estimate of what the seismic activity of Mars is. And this again is magnitude across here. So the bigger the magnitude, the fewer it is, because this is the number that happened per year. Okay, so this is 1 per year, 10 per year, etc. If any of you remember log paper, you can make everything fit if you put it on log paper because it scrunches everything down. That's what we did here. It's kind of cheating, but we can get away with it. What it actually turned out to be is this red kind of shaded area here, which falls right on top of our pre-mission goals. And that was fortunate because if Mars's activity was, say, down here, we would have probably not been able to supply NASA with its numbers, and they would have been coming after me. So here's the Earth up here, by the way. So Mars is about 1,000 times less active than the Earth, and it's about close to 1,000 times more active than the Moon. And again, that's kind of what you'd expect. Mars is a bigger planet than the Moon, smaller planet than the Earth, and so this is all kind of coming together. So those are kind of the big building block things that we wanted to do, but we're actually starting to be able to do things in a little bit more detail, looking at what we call the structure of the mantle. So there's the mantle is made up of heavy rocks, things called peridotite and olivine and things like that. They're a little bit heavier than rocks we usually get at the surface, but they have a lot of properties that make them interesting. One of the properties they have is that as they get under more and more pressure, the atoms will actually, at some point, rearrange themselves to pack in more tightly. So at the surface, you can have crystal lattices that have basically a lot of air in between. It's not air, it's vacuum at that level. But when you put it under pressure, they want to kind of get closer and closer together because they're getting squeezed. If you heat them up, they're vibrating, they actually want to hop back out again. So there's a sort of a competition between pressure pushing them together and temperature trying to pull them apart. And so where that transition occurs, called a phase transition, a solid state phase transition, that is able to pinpoint a pressure temperature condition. And so this little crick right here, you see this little kind of knee in the curve, and it's blown up here. That is actually this phase transition between two different crystal structures, and that actually tells us what the temperature is right here, because we know what the pressure is. We know what the pressure is just from the overburden. This tells us what the temperature is at this point in the mantle. And so now we're able not only to look at the physical structure of the mantle, but we're actually able to take its temperature not only at the surface, which we were trying to do with the heat flow probe, but we can actually take it here at a point very deep. And so that's one of the things we're doing. There's a whole bunch of other stuff. We have about 200 people on our science team that are, and most of them are seismologists, and they're going through this data. This data is also being put on a public depository. So if you want to start a new seismology hobby, you can actually go and pull our data off the internet. You don't have to have credentials, you don't have to have money. You just go to a site called IRIS, which is sort of a consortium of universities, and it's up there for anybody to look at and to analyze. And in fact, we are streaming this data out to about 24 schools across the Earth. Most of them turn out to be in France because France was the country that built the seismometer, and so they have a lot of interest in that. But we have schools in the US, and we actually were streaming the data to them more or less in real time. So before scientists outside our team had access to the data, which happens in about between 3 and 6 months, depending on the timing, school kids were already getting it and looking at it. And they were actually finding some of this stuff themselves, which was really cool. Okay, so there's something we were able to do that you can't do on the Earth. One is to actually look at the seismic signature of meteorite impacts. And this actually just came out just in the last few weeks. since Mars has such a thin atmosphere, a lot of very small meteorites get right through and hit the ground. Doesn't happen on the Earth very often, but we're actually able to look at these signals, and because they had some sonic booms associated with them, which we could also pick up on our seismometer, we thought that we could actually figure out that these were impacts. So we actually told the cameras on the orbiters to look in these places where we thought these things occurred, and lo and behold, we had before and after pictures. You can see here, like right there, it's before. You can see this little spot here. That's the after, before, after, before and after. So we're actually able to find these things from orbit after we found them seismically. And this is actually really cool because now we know the precise location of the epicenter of our Marsquake. It's not a fault Marsquake, it's a smash Marsquake. That actually allows us to calibrate all of our techniques for locating Marsquakes. So when we go through our incantations and stuff to figure out where a Marsquake was, we put a dot on the map. We don't know if we're right. It seems like we're right, but now we know we're right here, and we found out that we're able to verify that. So that verifies sort of the bigger picture. So all those points on the map are now much more solid than they were before. And these first ones we found are all very small craters. They're maybe anywhere from 5 to, I think the biggest one was maybe 20 feet across. And we thought that was really cool that we could see these craters on Mars. And then last Christmas Eve, we saw one of our largest Marsquakes to date. It's about a magnitude 4.2. It's so-called S1094b. I can't keep numbers in my head anymore. This is a little bit different because this was about 3,500 kilometers away. That's a long way. That's like Los Angeles from here. And it was big enough that we saw it not in the high-resolution camera, we actually saw it in the weather camera. So there's a camera that's orbiting Mars, and it takes these giant strips. Every single day, it takes an image of the whole planet, and the smallest thing it can see is about 5 miles across. That's 1 pixel. But this was big enough that it actually showed up in that camera, and since they take a picture every single day, we knew that they knew that it happened on Christmas Eve. And the people who took these pictures were on a different mission, but they had heard our report on the news that we saw this Marsquake on Christmas Eve. So they came and they talked to us. We compared notes. We said, well, where did you find this? And they said, well, latitude such and such, longitude such and such. And that was right in the middle of, well, not in the middle, kind of off to the side, but it was within the uncertainty that we'd picked up. And so we were able to actually show that this crater had been formed at this exact time, and we picked it up with our seismometer. This crater is 500 feet across. So it's like the size of Heinz or yeah, the stadium next door, right? It's about that size. It's a huge crater. And we'd only expect to see something like that happen on Mars every 20, 30, 40 years maybe. So we count ourselves super, super fortunate to be there when this crater occurred. We were just so happy until actually we figured out about 2 months later that there was another one that had happened about 2 months earlier. So once we had this one, started just for the fun of it, taking all of our big Marsquakes, taking images of the epicentral area, and we found another one. So now there's 2 of these craters. This one is only 400 feet across. Still, I wouldn't want to be standing next to it when it hit. So we have 2 big craters. They're only supposed to happen every 40 years. It's a mystery that we'll be working on for some time, but it's really cool to actually be able to see it with your eyes and have this Marsquake record, which is showing you how things happen, how that energy was developing and being embedded into the ground as a function of time during this impact process. So we're able to start to unravel the impact process as a dynamic process, as well as now not only calibrating our close-in seismic location, but now our locations all over the planet, because like I said, this one was 3,500 kilometers away. The second one we found was actually 7,000 kilometers away, which is 4,500 miles. So these are really, really distant quakes or impacts, and so it's really pulling together our techniques and our theories of how this stuff occurs. And I think, so go back to that figure, all those question marks. So watch this. It's like magic. Watch. The core grows. All the question marks go away. I can now write an encyclopedia article with actual numbers in it, if they actually ask me to again, because I was like 2 months late delivering this one, so they might not ask me again. But somebody else can do it because those numbers are public record now. So now Mars is on the same footing as the Earth and the Moon in terms of rocky planets. They're building blocks. Now the theoreticians who look at these differentiation processes can use what happened on Mars to test their models that they've developed for the Earth and the Moon and start to fine-tune them and understand how we got to where we are today. So it's getting late, but I have a little bit of status on the mission itself. So this is a blink between what the spacecraft looked like 10 days after it landed and what it looked like about 4 months ago. And you can see it's got dust on it. Mars is a very dusty place. Those solar panels are what actually power the spacecraft. We've gone, this is a power plot, so this is watts per sol, so, or actually watt hours per sol. So this is 5 megawatt hours per day that we were generating at the beginning of the mission. This is where we are 4 years later. We're down to around 300. So we're only putting out about 10%, less than 10% of our original array power. We've shut down everything except for the absolute minimum activity on the spacecraft. We're turning on the seismometer only every third day. This is a blow-up of the end of that plot. So here we are, we're coming around. At this point, there was a dust storm about a month and a half ago, and our power goes from 420 down here to about 280. At 280, we don't have enough power to recharge our batteries every day. So we've got some very nice batteries. They have a lot of capacity. So during the nighttime, they get used up by the computer and the seismometer. During the daytime, they get charged up again. But this is a voltage plot, and this is just, sorry, this is ugly. This is just what we get down from the spacecraft. This is the battery voltage. It's a 32-volt battery, so it's running up here around 32 volts. This is what happened with the dust storm. Suddenly, our voltage is going down every day, and we're only getting a few measurements because we're telling the spacecraft to sleep about 23 hours out of the day, and it just wakes up for about a half an hour in the morning, about a half an hour in the afternoon, so we only get these measurements when it's awake. But you can tell that the maximum voltage is going down, the minimum voltage is going down. This is what happens when we turn on the radio. That's our biggest energy usage. But we decided to keep the seismometer running because there's no point in having a lander sitting on Mars not doing anything. So what we can do, and this is a fun game. Are you an optimist or a pessimist? When do you think the spacecraft will die? Okay, so this is the slope of these voltages. This is technically when it will enter what we call dead bus mode. The computer will shut down. It'll go into a zombie mode, and we'll probably never hear from it again. But what happens when it hits here, suddenly the batteries start to discharge really quickly. So somewhere between here and here, it's going to go into dead bus mode. So if you're a pessimist, you draw a line like this through these points, and you look at these lower things, and maybe by the end of the month, you won't be able to talk to the spacecraft anymore. If you're an optimist, you skim along these points, and you go out to the end of the year, and if you're a real fantasy fan and you just believe in miracles and unicorns, maybe those solar panels won't keep getting dusty. Right now, when that dust storm clears, what usually happens is that you're trying to see the sun through all this dust. The dust goes out of the atmosphere and then the sun comes back. Unfortunately, where that dust usually comes is straight down onto your solar panel. So for 4 out of 5 dust storms, we get that big dip and then it just goes level after that because as the sky clears, the panels get dusty. But 1 out of 4, you come back up, perhaps even close to where you started it, because the dust actually falls somewhere else. We don't exactly know how to model this, but what's actually looks like it's happening, and just based on the stuff that came down this weekend that we were analyzing today, the solar panels do seem to be producing a little bit more energy. So maybe December 30th is the end of the mission. Maybe we can go out into January, but no matter what's going to happen, it's going to be sunset pretty soon for InSight. And that's all I have to talk about tonight. So thanks for listening.
Thank you. Thank you, everybody. We're going to be walking around getting questions from you, the audience. So if you'd like to go ahead and if you have any questions, raise your hand, and we're going to try to get to everybody if we can. And with Brad down front here.
And while you're thinking of those questions, another round of applause for Bruce here. That was fantastic. And if you want to keep the Mars learning going, this is absolutely the perfect time to remind or inform you, hopefully maybe not for the first time, that on the 19th of this month, we do open our new exhibition, Mars, the Next Giant Leap. And that is imagining a future for humanity on Mars, but maybe using that as a lens to look at life here on planet Earth too. So do please come on back to see Mars, the Next Giant Leap when that opens. And if we've got some audience questions here on site, we'll get those started.
I know we didn't want to talk about the heat probe, but got a question. Did the heat probe fail, or did the science that you were thinking it was going to be able to do not work out?
C. Okay, so the heat probe didn't fail, but it did fail to meet its objectives. And what happened was we designed the heat flow probe to penetrate into sandy soil that we had analyzed at the Viking landing sites, Viking 1 and Viking 2 back in the 1970s, at the Spirit rover site, at the Opportunity rover site. They all found similar kind of soil. It's a fine-grained sand, fairly loose, and we simulated that sand, and we designed our mold to penetrate through that kind of material. When we landed on Mars, it turns out we found something new, which was a soil, or what we call a regolith, that had sand in it, but it had two things happening which foiled our mold. One was there's something called a duricrust, and it was a crusty layer, probably about 5 or 6 inches thick. It's like dirt clods, okay? So it wasn't loose sand, it was something not hard, it was crumbly. And probably related to that is when you did crumble it, it had a lot of very fine material, the dust material, was mixed in with the sand to give it sort of more of a flour texture than a sand texture. And the mold depended on the sand kind of flowing around itself and providing friction so that it didn't rebound. So, the hammer inside would pop it down, and then the hammer has to come back up again, and that friction kept the whole mold from coming back up. But because of this crust and that powdery stuff, it ended up making a hole around itself, so it was kind of rattling around in this hole, and it didn't have enough friction to keep going down. And so we were able to, we put our scoop on the back of it. We spent spent a long time, a year and a half or so, trying to work this thing into the ground, and we got it down to where the back of it was flush with the surface, so we could kind of help it a little bit with our scoop, but that didn't get it deep enough to get it through this layer and be able to get a little bit of grip to go down. So we actually learned something about the soil of Mars. So now Mars isn't a uniform ball of sandy soil. We know that we have these other kind of pockets, and we think it's because we actually landed in a small filled crater that's about 30 feet across, just by coincidence. And that's probably got filled in from the wind, and the wind probably put in more dust than sand. And so, geologically, we're starting to put this together. So it's really interesting data. We're actually also getting thermal measurements of the thermal properties of that top, half a meter or so. So it's not a total loss, but it was a huge, huge disappointment. Well, by the way, I work at the Jet Propulsion Laboratory in Pasadena, but what we didn't mention is I actually live in Pittsburgh, so I actually commute every day to Pasadena via the magic of the internet, and so I moved here about 2 years ago. So this is my Pittsburgh debut, so thank you very much. but yeah, I'm a local, trying to learn how to say yints at the right time.
Simple question. Oh yeah. How liquid is the center core? You talk about the viscosity. If you guess what that is.
It's a very low viscosity liquid. It's essentially this similar to what the molten iron in the refine. What do you call them? They're not forges. Anyway, liquid iron. When you see it pouring, it's pretty much the same. Yeah. So the pressure doesn't really affect the viscosity too much. It turns out for iron. It is a little bit thicker, but it's still pretty runny. We think. We've done experiments.
Talked about the magnetic field, the absence of magnetic field on Mars. Is that related to the fact that the core is not solid? Or did it once have, a magnetic field, and therefore the atmosphere being thicker?
So that's a whole talk by itself. That's a really interesting subject, at least to me. It turns out the way that magnetic fields are generated in cores, planetary cores, is really interesting. So first of all, you have to have a liquid core because you have to have motion of charges, okay? And if it's just conducting, that's not enough. You have to actually have, the stuff actually moving around and moving the charges around. And so you have to have a liquid core, you have to have a planet that's rotating, and if you remember your high school E&M, if you move a charge, it creates a magnetic field. Okay, so why doesn't Mars have a magnetic field? It has a nice liquid core, has a nice rotation. And it turns out that it's not the whole rotation of the core that creates a magnetic field, but it's the turbulence, it's eddies. Okay, so as it starts turning, and you get Coriolis forces, and you get convection, you get material rising from the center of the core towards the outside, and that gets, the paths get bent by a Coriolis force, and that turns into these sort of cigar-shaped eddies, and those eddies are what creates the actual magnetic field. They're like little solenoids. We believe that Mars's core doesn't make a magnetic field because it's too hot, which seems like it's backward. And it's too hot because the mantle of Mars is not pulling the heat out of the core. If it was pulling the heat out of the core, it would cool the top of the core, and the molten, the iron at the top would fall to the center. The hot stuff at the center would come to the top, and it would create the eddies. But instead, the mantle of Mars is sluggish. It's not allowing the heat to escape very quickly, And so it's sort of it's an insulated core. If the core wasn't insulated, it would be losing heat, but while it's losing heat, it would be making a magnetic field. So that would also cause it to lose its magnetic field earlier, but it's already lost its magnetic field, so it's complicated. But it's fun, right? Complication is fun. So the modelers are just going crazy with this stuff because, again, the mechanics, the magnetohydrodynamics of this core stuff is really complicated, and so that attracts a lot of scientists.
So first off, thank you for your talk. But so if NASA let you fly another seismometer somewhere else in the solar system, where would you go, and what questions would you try to answer?
Well, I don't think there's a planet that wouldn't benefit from a seismometer. Right? I haven't met a planet yet that I wouldn't want to put a seismometer on. But there are actually things that are happening in other planets and places. There's actually a seismometer getting ready to fly to the moon. Okay, so we did the moon, right? Apollo did the moon. 4 seismometers that worked, and a lot of great data. But there's a lot of open questions on the moon, especially since those were, seismometers and the electronics that go with them were made in the 60s, and the data is actually really, really batty. And it's concentrated. All the Apollo landings were concentrated sort of right next to the Earth. And so we don't know much about the moon globally. And so there's a lot of things that we could benefit to the moon by sending a modern seismometer, perhaps particularly to the far side. And I have a friend who's actually using one of our spares from InSight, because when you build a seismometer, you build a spare just so that you don't end up, if you drop it, you're not out of luck. So anyway, he's taking the spare and he's putting it on a lunar lander. He's actually in the Astrobotic was in competition with a couple other providers to take it, but a place up in Boston got that particular instrument. So it's going to the far side, and so that's one thing. There's a seismometer going to Titan on the Dragonfly mission. So the Dragonfly is a helicopter, not the best platform for a seismometer, but it lands, and while it's landing, we think Titan's probably a pretty seismically interesting planet. It's got oceans, it's got a lot of tidal flexing going on, so it's kind of a afterthought instrument. It's not a super sensitive one, but so that could be interesting. The place to send a seismometer, an interesting place to send a seismometer would be Europa. So Europa is really interesting because it's got an icy shell that's 50 or 100 kilometers thick and an ocean below. And so the properties of that shell are really interesting because it's an icy planet. Plus, that's the sort of the next best place to look for life. And if you understand the composition and the dynamics of that shell and the ocean underneath, you know a little bit more about the conditions for life. So that's a really cool place to send a seismometer. At one point, I had a proposal to send a seismometer to a comet, which would be really fun because you could watch the comet break up and jet around and stuff like that. Enceladus would be a cool place because you've got these plumes that would create seismic activity, and you'd be able to probe the interior of Enceladus. And Io, Venus, I'd love to send a seismometer to Venus if it wouldn't melt. That's probably the holy grail right now for planetary seismology is Venus.
What surprised you the most? And how is all this
come back to Earth and how we understand our own planet?
The thing that surprised me the most, well, the thing that surprised me the most was that I didn't hear a Marsquake I didn't hear a Marsquake for 3 months. That was a big surprise. But scientifically, the core size, that really surprised me. I thought that it was going to be much smaller. I don't understand how you can get as much sulfur into the core as you need. You need about 15 to 20% sulfur, and all the models of planetary formation kind of max out at about 12%. So we don't know how to get that much material into the core. You know, when the iron comes down, it kind of leaches stuff out of the rocks as it goes down, but we feel like we understand how that chemistry works and how the physics works, but it's done something else. So that is really surprising, and that's going to take a while to figure out, I think. So that's the most surprising thing to me. Actually seeing a crater actually happen on Mars, that was a surprise. That was a big surprise. I'm glad it didn't happen closer.
We have a few questions from our online viewers. The first one is from Adam. Is the grouping of seismic activity around Cerberus Fossae possibly a lingering effect of the hypothesized colossal northern hemisphere impact event, which is also thought to have created Olympus Mons, the Tharsis Montes, and Valles Marineris?
Possibly. So Adam's talking about the so-called crustal dichotomy on Mars. The whole northern half of the planet, or northern third of the planet, is about 4 or 5 miles lower in elevation than the southern highlands, and it's a different composition. And there are several theories as to why that is, and one is that there was a big impact early in Mars's history that just essentially made a crater that covered a third of the planet. And Cerberus Fossae is kind of on the edge of that, kind of on the edge of Tharsis, which is the other interesting thing about Mars, is this big volcanic province that's a huge pile of lava with these giant volcanoes on it. And Cerberus Fossae is kind of off of that. It's kind of off the dichotomy boundary. So it doesn't really line up with either of those things, but it's likely that it's tied in somehow, because those things are big enough that they really affect almost everything that's going on Mars. But we really don't understand exactly what's happening now, what's happening yet. Fortunately, like I said, we collected this data. We've really only scratched the surface. I think people are going to be analyzing this and getting new results out of it for decades. And hopefully that's one of the things that come out of it, is trying to put together sort of a large-scale integrated geological understanding of activity on Mars.
Aaron asks, how much coordination exists between various different projects active on and around Mars? I imagine you'd get an official heads up before another project would bounce land another probe off the surface, no?
There's a lot of coordination, both on the scientific level. I mean, the scientists talk to each other all the time. On the project level, at least in the US, most of the Mars missions are run out of Jet Propulsion Laboratory, so the project offices are on different floors of the same building. So there's actually a Mars program which exists basically to make sure that we get the advantage of coordination between these projects. There are also Mars projects from the European Space Agency. There's a pair of orbiters that are going around Mars right now from ESA, and there's very good coordination between them and NASA. And again, the science teams, there are basically no boundaries between science teams. You can't keep a scientist quiet. They'll just talk to each other no matter what you do. There's a mission from the United Arab Emirates. There's a mission from India, and my experience is that the communication channels between those missions are not quite as transparent, but still, we're talking to each other. There's official coordination at the kind of agency level, and there's scientific coordination at the sort of the worker level. So there is a lot of coordination that goes on with the missions.
All right, we have one more question online from David. Why do you think that it is S dissolved in the iron? Why not some other elements?
If you take a rock and you get it really hot and you melt some iron and you percolate the iron through the rock, it turns out that the solubility of sulfur is really high at those pressures and temperatures. There's quite a bit of sulfur that's available in a carbonaceous chondrite meteorite. You can also get things like carbon. You can get potassium, phosphorus, oxygen. All those elements can get dissolved, but it's basically just the solubility, which is just like, solubility of things in water. If you put sugar in cold water, it doesn't dissolve very well. You heat it up, it dissolves better. That's just a variation in solubility. You have solubility of all these other elements into molten iron, and the solubility of sulfur at the conditions, at least inside of a planet, tend to favor that being absorbed into the melt.
Are there any depictions of Mars in various media that you find to be particularly accurate, or any that you find to be particularly inaccurate?
I'm sorry, I didn't quite.
Are there any depictions of Mars in various media, say books or movies, television, that you find to be particularly accurate or particularly inaccurate?
99% is particularly inaccurate. The Martian is just about spot on. I mean, the movie The Martian is really close to, as close to reality I think as you can get with a movie. The only thing in The Martian, the dust storm, is complete baloney. I mean, if you a raging dust storm on Mars, you could walk out and you get dirty, and you could probably feel a breeze, but that's about it. You don't have the violent winds that they have on the dust storm. But other than that, and the fact that when this little thing explodes and pushes it back, that would have shredded its entire enclosure. Those are the only two things that I thought were bad. Other than that, the way that the missions work, the way that the recovery was done, the orbital mechanics of the rescue and stuff was spot on, which is really weird. What I guess the movie that annoys me the most is Gravity. Gravity is horrible. The physics are just completely, and Lost in Space. That's more fun than Gravity.
We have a question all the way up top.
Earlier in the presentation, you mentioned that Neptune was a point of interest. Could you elaborate on that? And whether the work done on Mars, how, if at all, that would apply to something like Neptune, a Jovian world?
So Neptune is really interesting because Neptune and Uranus both are ice giants. So when I was in school, I learned that you had the gas giants, Jupiter, Saturn, Uranus, and Neptune. But it turns out Uranus and Neptune are very, very different than Jupiter and Saturn in that they are mostly ice. They have a gaseous envelope on the outside, but mostly they're ice. And they're sort of the key to the formation of the solar system in some ways more than Jupiter and Saturn, because having formed farther out, again, they're a little bit more pristine. They retain more of what we think will be the fingerprints to understand how the solar nebula sort of coalesced into the planets. The other interesting thing about Neptune is that it's sitting on its side, right? The rotation axis is in the plane of the orbit instead of being sticking up sort of solar north like everything else. And so that's a dynamical puzzle that's really interesting. And it has some really cool satellites, which are more interesting to me because the satellites are more like planets that I'm accustomed to doing. Mostly though, I'm just a fan. I don't have a lot of scientific firsthand knowledge of these things, but I go to talks, I listen to things. So mostly I'm just a fan. And how does the stuff on Mars come back to Earth? That's a tough question. I mean, if you're looking for direct, benefits, there's not a lot of direct benefits of planetary exploration to sort of practical benefits on the Earth. But I do feel that the benefits are still very, very real. The benefits of exploration, not in terms of colonization and planting flags, but exploration in terms of understanding, the universe around us. The things that we end up understanding about Mars and about Jupiter, about Neptune, always come back and help us understand more about our planet. And you can argue maybe about, again, how practical understanding our planet is, understanding, how Earth formed, how a habitable environment on Earth formed. There is some benefit in terms of understanding climate change. So when the climate's changing, we have theories and models about how that interaction works, what the systems are and how they work. But it's a little bit difficult to refine those models if all you have is one example. So to get to the future, when things are going to be different, if all your model knows is what has happened in the past, you're on a little bit shaky ground or thin ice. If you have those models to apply to other planets with other situations, you can find out, okay, when you extrapolate it to Mars, it doesn't work. Well, why doesn't it work? It's because you haven't taken these parameters into account, or these equations are not the right equations. You fix those, and that actually helps you to take the Earth and change the conditions a little bit and look at the future. So in the sense that the more we understand about the universe, the more we understand about the Earth, the more we understand about the Earth, the more we'll understand about how what we do affects it. So I think that's probably the best benefit, or the most concrete benefit.
This may sound a bit silly, but is it possible to shake off the dust that's accumulated on the panel, like similar to some of the stuff which is ongoing in like the Saharan desert, for example, where you have strong winds as well and dust getting accumulated on the solar panels? Would any of those solutions be applicable?
There's a fan back here. I have a hard time here. Yeah, I think probably so. I mean, the problem is that there are actually a lot of solutions that you could implement to keep solar panels clean and extend emission. But $800 million sounds like a lot of money, but actually that's a shoestring budget to go to Mars. Our mission is in this Discovery program, which is kind of the bargain basement of NASA, and it takes almost all that money just to get to Mars. And so when we start looking at extra stuff, bells and whistles to make things better, the budget is just not really there for a mission of this size. One of the reasons why we said we could do it in 2 years is we knew that our solar panels were going to get dusty. And so if it was going to take 5 years to answer those questions, we didn't have a mission without doing something else besides solar panels. Our solar panels turned out to be really cheap because they'd already made them for a previous mission. In fact, our whole spacecraft was just a recycled Phoenix lander, which allowed us to kind of get into that, into the budget box. But to put something like a compressed air blower, which might have worked, or some kind of a grid of of electric wires that could, electrostatically, remove things. That's all stuff that we could have done. But in order to develop it and to test it and to be able to fly it on our mission, it probably would have cost us another, 15, 20% of the mission cost. So we made a trade-off saying, we can do this. It'll last 2 years for sure, and it should last longer. We gave it some margin, and so that should give us our science. And so that's what we did. So in retrospect, yeah, I wish we'd had something to do the panels because I'd like to see more data. But I also know that we proposed this mission to do this science for this amount of money. That's kind of our contract. We fulfilled our contract. Our spacecraft fulfilled its contract. NASA gave us our money, so it's fulfilled its contract. Everybody's happy.
Great, and we've got our final question over here.
This was a really interesting talk, thank you. Is it possible for the molten cores of planets to solidify and cool over time, or does the pressure prevent that from happening?
Yeah, the planetary cores definitely cool over time, and as they cool, they solidify, they crystallize. The pressure actually helps that. The pressure, it'll solidify quicker under pressure than it will without the pressure. But every planet is losing its heat. It's a heat engine. It's got energy. It's losing that energy, and as it cools, the materials are going to cool inside, and things that are molten will eventually crystallize, will solidify. So turns out even the moon has an iron core that's molten, which is kind of a surprise. It's really tiny. But eventually, even the Earth's core will solidify. Right now, the solid core in the Earth's core, the inner core, is actually growing, and it'll grow over the next, 4 billion years or so, and eventually the whole core will solidify. That'll be fun.
Thank you, Bruce. That was fantastic. Thank you all for being here tonight. I would love to be the first one to invite you all to join us right back here next month, the first Monday of December, for our next speaker, Dr. Ira Rothstein from Carnegie Mellon University, who has an app that he's developed to teach people about relativity without any high-level math involved. So if you're interested in physics and relativity, come on out for that. And then our speaker for January is Christine Roman-Lansky, who will be talking about, I've got it right here in my pocket because I knew I was going to forget the acronym, CVI, Cerebral Visual Impairment. So come on out for our next couple of speakers here. Café Sci is typically the first Monday of the month, and we'll see you all again next time. Thank you, everybody. Don't forget to grab your stickers.
This one wasn't in the battery diet. It's not.